Today we're working in section 3.2 and we're going to be back at the track. In section 3.1 we looked at the relationship between the 40-yard sprint time in seconds and the long jump distance in inches for a small statistics class with 12 students. A scatter plot with the least squares regression line y hat equals 414.79 minus 45.74x, and a residual plot are shown below. Also, s equals 22.38 and r squared equals 0.702. A lot of times with these problems, they're going to give us a lot of information like this, our graphs and our data, because doing it all by hand or even with the help of a calculator can be very time consuming. So when we have this much information, it's our job to be able to interpret it all, really showing that you understand what's happening. So our problem that we're going to start with in part A is to calculate and interpret the residual for Christian, who had a sprint time of 7.25 seconds and a long jump of 110 inches. So 7.25 with 110 looks like we are looking at this point right here. Now if we're going to calculate the residual for him, the residual is the observation minus the prediction. Now we know what our observed value was. We know that there was a long jump of 110 when we plugged in our sprint time of 7.25. We just need to find out what our prediction is. So we're going to use that y hat because that stands for the predicted long jump, and that was given to us up here, 414.79 minus 45.74. We're going to plug in our value that we have. And then, yes, with the help of a calculator, you're going to simplify that and you get 83.175. So it was predicted to be about 83 inches, but it actually was about 110. So that's where our observation comes from, or I'm sorry, our residual comes from. The observation of 110 minus the prediction of 83.175 gives us our residual of 26.825. And as always, we're going to give that answer in context. So Christian's long jump was about 27 inches longer than expected based on his sprint time. Moving on to part B, is a linear model appropriate for these data? Explain. We can look at the graph and tell they appear to fit a line pretty well. When we draw in our least squares regression line through it, they all seem to be pretty close to that line. But being able to confirm what we're seeing visually, we use our residual. That gives a little bit more support to our claim. So looking at a residual plot, we want to look for a scattering of the points. If we see a scattering of our points, that means we're missing by a random amount above and below. We want to be missing by a random amount. We don't want to miss in a pattern of any sort. If we're missing in a pattern, that means that there was a pattern to begin with that's something other than the line that we've drawn. So because we see a scattering there, we would answer that because there is no obvious pattern left over in the residual plot, the linear model is appropriate. Then I'm going to move this up so we can see some more here. Part C asks us to interpret the value of S. Now up at the top it told us that S equals 22.38. Then you have to recall that S is the standard deviation of the residuals. I'm sorry, you might be able to hear those dogs going crazy in the background. Those are not my dogs, those are a neighbor's dog. So S is the standard deviation of the residuals. If you think about standard deviation, we're thinking about on average how much it's missing from our mean is what we usually think of, but this is standard deviation of the residuals. So on average, how much is our least squares regression line missing? So if our least squares regression line is our prediction, how much is it missing the actual observed values? So when using the least squares regression line with x equal to sprint time to predict y equal to long jump distance, we will typically be off by about 22.38 inches. And then finally, we're going to interpret the value of r squared. And again, up top, we were given that r squared is equal to 0.702. Now, remember I said before that it looks like our points are pretty close to that line. That means that we would probably have a pretty strong r value. Now, it was negative, so if you remember from videos before, we found that we had a negative 0.84 correlation. R squared is literally squaring that value and getting what it is. But R squared has a different meaning. Remember, it was our coefficient of determination. So we have 70.2% of the variation in long jump distance is accounted for by the linear model relating long jump distance to sprint time. In other words, there can be other things involved. Maybe it's not just sprint time and long that helps us to predict the long jump. It could be things like the height of the jumper or the experience of the jumper. Different variables can play a role in this, not just the sprint. So when I'm looking at my least squares regression model, when I'm using this model to predict jump, it's accounting for about 70.2% of that variation that's happening, which means there's other variables out there that are accounting for the remaining 30 or so percent. So again, being able to do the calculations is good, but because a lot of those take a lot of time, you're going to have questions more like this, where a lot of things are given to you up front, and it's your job to be able to interpret them.